right? So let us see the power relationships in AC circuit, how we deal the AC circuits. So prior to that, just let me give you for DC circuit, for a DC circuit, how we write the power. What is the power concept? The power in any DC circuit is given by voltage into current. So voltage, or let me write in generally like voltage into current VI, or it can also be written as I square into R, or it can also be written as V square by R. This is what the power relationship in any DC circuit. Now if we see the power concept in the AC circuit, so as because the voltage is continuously varying and also the current is continuously varying, so this V of t and I of t are referred as instantaneous values of voltage and current in AC circuits. Like just you can understand that in DC circuit voltage is constant and current is constant, thereby power is constant, which we got as simply V into I. But this voltage and current both are varying with respect to time, as because of that I am writing this as V of t and I of t. Then how we write the power in AC circuit is as like in DC, which is product of voltage and current, but try to observe everything I am writing in small case letters. These small case letters represents instantaneous. So the power in AC circuit can be written as P is equal to V of t into I of t. Now as because power is continuously changing, as voltage and current is changing, so we need to do something. What we do? So when we introduce the AC circuit, if the voltage is continuously changing, it is difficult to define some of the situations. So we introduce terminology like average value. We identify the time period and we evaluate the voltage over that particular time period and we see how much is the average. And we say that AC voltage has certain average value. In the same way, we apply the concept of that average value to this time varying power. So what I will say is that the average power over let us say over a period t. How we write the average value of any function over a period t? So that I will represent as capital letter P, which is equal to 1 by t integral over 0 to t small p dt, which is equal to 1 by t integral over small p is V of t into I of t dt over 0 to t. So in this way we can find the average power in the AC circuit, as because the voltage and current is time varying in nature, so the power also varies with respect to time. But in order to define particular value of the power like some constant value, so we evaluate the power over a period, so which gives P is equal to integral over 0 to Vi dt by t. So this average power can also be called as active power or it can also be named as true power. This terminology is very important, and which is measured in watts, W. Okay. So now we had seen various circuit elements and we know its characteristics. Like, let me write in summary as like this. We had seen initially when we introduced the resistive element, inductive element and capacitive element. For these three, what nature we see? Tell me. For a resistor, voltage and current both are in phase, yes or no? Whereas for a inductor, current lags the voltage by 90 degrees. This red color one is the current and blue color one is the voltage. Whereas for the capacitor, current leads the voltage by 90 degrees. So this is the voltage across the inductor, capacitor, resistor. Now based on this idea, just I can write simply in this way. If we assume that if voltage is V is equal to Vm sine or cos, it doesn't matter, sine omega t, then as because current is also in phase with the voltage for the resistor, I can say directly I is equal to some value as Im sine omega t. Here if it is 0, here also 0, directly omega t. Now same thing can I write for the inductor? If the voltage is this much, that Vm this thing, and for the capacitor also if this is the voltage, can you write the currents? So for capacitor, can we write the current as like this? I is equal to Im sine omega t. Tell me. Omega t minus or plus? Minus 90 degrees, so that it is lagging. And whereas for the capacitor, I can write Im sine omega t plus 90 degrees, so that current is leading. If these are the voltage current relationship for the resistor, inductor and capacitor, now we can quickly evaluate how much is the power. So for resistive case, let us evaluate the power. Small p is equal to small v into small I. So quickly evaluate these things. So Vm sine omega t into Im sine omega t. So this is what the power. So can I write this as Vm into Im sine square omega t, and this can be further written that, so Vm Im sine square can be written as 1 minus cos 2 omega t by 2. So this is what the power, and see this power is time varying power. What we do in order to get the some power, the power in AC circuit we define as capital P as integral over 1 by t 0 to t small p dt. Just we evaluate the average power. The average power can also be called as a true power or active power. True power. See that how much we will get if you integrate this. So what we get, this is magnitude is Vm Im by 2, which comes out, and t is there, so t integral over 0 to t. How much we will get? This 1 minus cos 2 omega t dt, and evaluate this second term goes 0 and first term will become t. So ultimately what you get is Vm Im by 2, which can be written further that Vm by root 2 into Im by root 2. What is Vm by root 2? Vrms. So Vrms. What is Im by root 2? Irms. So usually we write RMS values as capital case letter directly as V into I. So magnitude of the voltage RMS value into magnitude of the current RMS value is what the active power or true power for resistor. True power for resistor. What about for inductor and capacitor? Can you do the same exercise? Let me do only for inductor and I will leave the capacitor part for you. So now for the inductor, Vi is the power, and how we get this? So Vm Im into, let us say this as sine omega t into sine omega t minus 90 degrees. So you can make this simplification and you can write, so sine A sine B, that is 2 sine A sine B you can write. So so or you can make this into cos form, then you can write 2 sine A cos B and you can explore that and you can integrate that. And just I am leaving this part because these are general mathematics, so let me cover some other parts. And just finally I want to conclude this. So after just simplifying this expression some extent, what we do is that we try to find the average power, which is 1 by t integral over 0 to t p small p dt, which gives here as 0. This you verify. This becomes 0. Similarly, for capacitor also the capital P will become 0. These are the two important points, that active power or true power for a pure inductor is 0. Similarly, the reactive power for a pure capacitor is 0. Clear? So now, then if the active power is 0, is there any other power? So why? Because this element is existing in the AC system, like in the circuit, and it has its own reactance as XL, it has its own reactance as minus JXC, but there may be certain power as like this. So that is what the reactive power. So the reactive power is defined as Q is, just don't get confused with that quality factor with this reactive power. Reactive power, this is for reactive elements. Let me write for reactive elements. For reactive elements, the reactive power is represented by the letter Q. How much we will get is that as like this, Vm Im by or let me say Vm Im by 2, as like in the active power case. So see, Vm Im by 2 for the resistor, which is active power. In the same way, so there will be certain power. I will show why we get this kind of expression just a little later. This is what the V into I, that is Vrms into Irms. And what is V here is that, what is V for inductor is that, let us say, so V, can I write I into XL? I into XL. So if it is I into XL, then the reactive power will become I into XL into I, which is equal to I square into XL, which look like I square into R. See, for resistor, how much is the power? I square into R. In the same way, for reactive elements, how much is the power? I square into its reactance, which is XL. And this can also be written as if I'll write I as V by XL, then I can write this as V square by XL. The reactive power can be written as Q is equal to I square into XL or V square by XL. If it is capacitor, for capacitor, V is equal to I into XC, thereby the power, the Q is equal to I square into XC or simply V square by XC. And the units for this reactive power is volt ampere reactance, VAR, volt ampere reactance. So this is the generalized concept that if the active power for the L and C is 0, then is that means that the generalized power, complete power is 0 across that element? No. It has certain power. How much is that power? Is I square into XL or I square into XC. That power we call as reactive power, which is contributed by the reactive elements. So instead of all these things, now just I will give you some generalized principle which is very simple to understand the concept of power. Let me write. Instead of like whether it is resistor, inductor or capacitor, we don't know what is that. Whatever may be the thing, whatever may be the element, it doesn't matter. Now how we deal the power concept in AC circuit is that, let me write, in general, if we have, let us say, as V of t is equal to Vm cos or sine, it doesn't matter, something, omega t plus 0 and or let me say instead of 0 as alpha, I of t as Im cos omega t plus beta. So voltage has an angle of alpha, current has an angle of beta. What I'll do is that just I will try to convert these things into phasor form. I'll write as V bar is equal to V at an angle of alpha, where V is the RMS value, which is VRMS. Once we know peak magnitude, we can write RMS value as Vm by root 2. Similarly, the current also I'll write as I bar is equal to I at an angle of beta, which is where I is equal to IRMS, which is equal to Im by root 2. Peak value divided by root 2 for sinusoidal is the RMS value. Now let us see that how we deal the power in the AC circuit in terms of complex numbers. So in AC circuit, the power concept is dealt with complex values. So here I will write that complex power is generally represented by the letter S, which is defined as simply voltage phasor, current phasor magnitude, voltage phasor, current phasor product, but current conjugate. This is very important. Current conjugate. And one should understand the conjugate concept that A plus JB whole conjugate is A minus JB, or R at an angle theta whole conjugate is magnitude same but angle will become negative, like R at an angle minus theta. This thing you should understand. Now we already have voltage current in the form of phasors, so we can deal these complex powers simply as V at an angle alpha into I at an angle beta whole conjugate is what the complex power. Now we can simplify this as V at an angle alpha into I at an angle minus beta as with this principle. So we can multiply these two phasors. We can write Vi at an angle of alpha minus beta. So try to observe the complex power S has two important factors. One is magnitude, another is angle. One is magnitude, another is angle. The magnitude of the complex power we call as apparent power. This terminology just try to understand. Apparent power, mod of S is referred as apparent power, which is equal to V into I. Voltage units is volt, current units are ampere, so volt ampere are the units. VA, simply we can write as VA are the units, volt ampere. Okay, these are the units. Next is, we already know that if something is R at an angle theta form, we can convert this polar notation into like rectangle form as R cos theta plus J R sin theta. Now is it looking like here magnitude is Vi, angle is alpha minus beta. Now can I convert this complex power S into as Vi cos alpha minus beta plus J Vi sin alpha minus beta. And instead of writing every time alpha minus beta, I will consider, so let theta is equal to voltage angle minus theta current angle. How much is the voltage angle is alpha, how much is the current angle is beta. Current angle is beta, you can verify back. Voltage angle is alpha, current angle is beta. Difference between that is I am assuming as theta. So now I can write this complex power as Vi cos theta plus J Vi sin theta. Now it comes here in a simple way that this complex power has real part and imaginary part. So this can be written as real part as capital P, imaginary part as capital Q. This is what the complex power. S is equal to P plus JQ, where P is referred as active power, which is equal to simply Vi cos theta, whereas Q is referred as reactive power, which is equal to Vi sin theta. And here you can define one more important thing that previously we already defined. The power factor PF can be defined as the ratio between the active power to apparent power. What is apparent power? Magnitude of the complex power. So what is the active power here is Vi cos theta, see here, divided by what is the apparent power is Vi, which is equal to simply cos theta. That's why previously when we dealt about this power factor, I had written directly as cos theta. How we got this cos theta is the ratio between powers. Which power? Active power to apparent power ratio is referred as the power factor. Clear? So this is all about the power concept in AC circuit. Just now let me take one example and with that let me wind up. So just let me take one simple problem as right. So okay, so let me take this way. A voltage V of t is equal to 100 sin 314t is applied across, just understand that is applied, I am not writing completely problem, is applied across series circuit consisting of, or let me draw with the help of that, a resistor and a inductor and a capacitor. For this circuit, we are applying a voltage of V of t. A voltage V of t is applied across the resistor. How much is the resistance? So 10 ohms. And how much is the inductance? Is 0.0318. How much is the capacitance? Is 63.6 microfarad. Now what we need to calculate is current I and the theta, which is the angle difference, phase angle difference between voltage and current, theta V minus theta I. This also we need to calculate. And we would like to calculate how much is the P, how much is the Q. So let us see how we do that. Okay. So these things what we required. Of course, we can calculate power factor, apparent power, etc. all those things. So now first thing what you need to observe is that given circuit has R, L, C elements in which L and C must be expressed in terms of the impedances as JXL and minus JX. That first observation you need to make. So for which I need the omega. How much is the omega? 314. How I got? From this voltage. The moment you will get, you can find XL is equal to omega L, which is equal to 314 into 0.0318. How much is this? Calculate. Similarly, XC is equal to 1 by omega C, which is equal to 1 by 314 into 63.6 into 10 power minus 6. How much are these values?
9.9852.
9.9852. Don't give me the wrong values. So just let me verify. 314 into 0.0318. Yeah, 9.9852. What about this value? So 1 divided by 314 into 63.6 into 10 power minus 6.
50.07.
Yeah, very good. 50.07 ohms. Now I got these two. Can I get the total circuit impedance? Z is equal to R plus J into XL minus XC. So R is, how much is the R? R is 10 plus J, XL is 9.985, XC is 50.07. So how much I'll get this in polar form? Check it. So 10 plus 9.985 minus 50.07 I. So actually I haven't kept in complex mode. Right. Okay. Anyhow, just to tell me how much is this value? 10 minus 50.07 minus 9.985. 9.98. Right. How much is this value? 40.085 J. You can express this in polar form also. 10 minus 40.085 I is in polar form 41.313 at an angle of minus 75 degrees. 75.99. Okay. So this is what the impedance. Now it is so simple that we already have voltage. How much is the voltage? 100 sine 3140. So can I write that voltage into voltage phasor? So as 100 by root 2 is the RMS value, angle is 0. So how much is 100 by root 2? Is 50 root 2, which is equal to 70.7 at an angle 0. Now see that for this circuit, if I want the current, I can write this voltage divided by total impedance, we already seen this kind of problem. Voltage divided by impedance, that is 70.7 at an angle 0 divided by, so how much is the impedance? 41.313 at an angle minus 75.99. So how much we will get? This is 70.71 divided by 41.313 at an angle of minus 75.99. Check it, how much you will get. I got this as 1.71 at an angle of 75.99 amperes. Now it is easy that, see, just compare these things as like this. V at an angle alpha, this is I at an angle of beta. Now whatever you need, you can calculate. What I need first is current. Current is magnitude is already there. I bar magnitude is equal to I. How much is that? 1.71 ampere. Next is theta. So how we get the theta? Second one, how we get the theta? Theta is equal to voltage angle minus current angle. How much is the voltage angle? Alpha. Alpha is equal to 0. Let me write alpha minus beta, which is equal to 0 minus current angle is 75.99. Next is P, active power. Can I calculate active power as like this? P is equal to voltage magnitude into current magnitude into cos theta. That what we had derived. See here in the above case. P is equal to VI cos theta. What is V? Voltage magnitude. What is I? Current magnitude. These things you should not lose the importance of VI. Okay. How much is V? V is 70.7. I is 1.71 into cos of 75.99. How much we will get? Cross verify. Q is equal to simple VI sin theta. So V is 70.7 into 1.71 into sin 75.99. Of course, we will get this as negative sign. So how much is these values? Just tell me and we will wind up. 70.7 into 1.71 into cos of 75.99. So this active power is equal to 29.268 watts, whereas reactive power is equal to, tell me, sine, so this become minus 117.3 volt ampere reactance units. If you need the apparent power, mod S is equal to V into I. Simple, 70.7 into 1.71. So how much we will get? Apparent power is 120.897 volt ampere. These all units are very, very important. So in this way, you can deal the power in AC circuit, and try to observe that up to this what we had seen in the previous concept, like when we deal with like RL circuit, RC circuit, we calculated theta, we calculated current, we calculated voltage. Now what extra are we doing is just using this PQS to get the active, reactive and apparent power. Okay. Thank you all.